ready? You ready, right? Opponent? You good already?
I'm ready.
Everyone ready? All right, good. It's about time to start second fight. As usual, I will start with introducing a jury member. First one is Professor Li Guanqing from Dak. Second one is 詹传忠教授 from 东海。朱立教授 from 中原。
太多了。
李野教授 from 东亚。周德来教授 from 中原医。周金武 from 彰化师大。All right, so let's start from reporter. Introduce your team and your team, please.
So we are the no-hiders of the American School. Ryan Cho, Posh, Eric, David, and Luca.
All right, thank you. Opponent, your
Hello everyone, we are Team Excelsior. I'm the captain He Su-Te, and this is Lin Peiyu, Cai Mu-en, Wu Junting, and Cai Xinzhang. Thank you.
all right, thank you. Review.
We are 电到下载是这样，瑞纯、万伦、羽绒、维锦、右维。
All right, so let's start the first stage. Opponent, you got 1 minute to challenge reporter for one problem. The group problem is out on the slide. All right. Oh, okay. Yeah, challenge one problem. Opponent? Problem number 2 is challenge. Reporter, you got 1 minute to make a decision. Problem number 2.
Yes, sir.
You accept it? Robert, accept it. So reporter, you got 5 minutes to prepare for your presentation. Please have your representative's name on the blackboard, please. You may begin.
Okay. I am Ryan Cho, and I'm presenting problem 2, Hibiscus model. Problem statement says that put a lid handle behind a bottle. If you blow from the bottle, then on the opposite side, the handle may go out as if the bottle was not there at all. Explain the phenomenon. So we have 3 main focuses in this problem. Our first focus is how does the Coanda effect allow this phenomenon to occur? Second focus is what are the properties of the velocity field behind the bottle? The third focus is how do parameters such as the distance away from the bottle and the bottle size impact this phenomenon. So, for example, So we're breaking this phenomenon explanation into 4 parts. First is phenomenon investigation, theoretical model. Then we're going to do experimental discussion, and then we're going to give a phenomenon investigation. So this is the wind blowing without the bottle. And then with the bottle, the handle is also blown out. So the Coanda effect is, let me give a brief explanation of the Coanda effect. The Coanda effect is caused by, says that a jet of air will travel along a surface. This is because on the side of the jet of air is a region of low pressure, and this low pressure causes some air on the surrounding sides to go into that jet of air, making that jet of air bigger. However, when the jet of air is going along a surface, this low pressure zone actually causes the ambient pressure to push down onto the surface. This causes the jet of air to go onto the slack to be sticking onto the surface. The Coanda effect occurs as air passes through this cylindrical bottle, as you can see there. And the handle will blow out because there will actually be 2 streams of air. And the 2 streams of air will meet together, and then they will be split and then meet together at the end here. And this will cause the flow to be relatively fast. So theoretical models. In part 1, we used the CFD, computer fluid dynamics simulation, to gain insight on this problem. What we did was we used the K omega turbulent model. The K omega turbulent model can provide closure to the Reynolds average of the Stokes equation by modeling turbulence with 2 factors, which is K, the turbulent kinetic energy, which depends on the average velocity of fluctuation, which is the turbulent energy. So the energy associated with vortices and eddies. The omega term is the rate at which K dissipates into the moment. And the equations aren't that important because we have a software that can help us model this. From FreeCAD, we made this geometry file. And then using FreeCAD, we put the CAD file into SimScale, which is a graphical user interface online. And then that took care of the meshing, boundary conditions, and simulation of the CFD, the computer fluid dynamics. And then it also helped us to visualize what you just saw before. And then I then used CareView for advanced visualization and data extraction from the simulation.
Excuse me, I'd like to mention that you can use this board.
Oh really? I don't
think
have
you
a
got there's a point in the text. Right?
No, there are no pointers to my desk. Can you pause the time?
Yeah, sure.
Okay.
I suppose that every team has there's a point, right?
I'm sorry, but actually,
You don't?
Thank you.
怎么没有？
oh,
I suppose you have one, yeah.
oh,
I think he wants a clicker. He doesn't.
But that's fine.
okay.
Okay, yeah, that's
Okay.
all right. So let's resume the.
Okay. And through CareView, we extracted the data from the CFD and made sense of it. So the first insight from Reynolds number is that the system is turbulent. Reynolds number we calculated is greater than 5 × 10⁻³ Kelvin. So it is guaranteed to be turbulent. But CFD provides us direct evidence that it is turbulent because of these vortices at the end of the cylinder that we see after wind blows through here. So this is direct evidence that vortices are formed behind the cylinder where the two streams flow around the cylinder, and then there's a space between it in which it's turbulent. And second insight from the CFD is that the velocity never reaches a steady state. As you can see here, the velocity field actually fluctuates wildly with time. However, if you time average the velocity, you actually get a very unique shape, which is the velocity reaches from a minimum value up, a small value up to a maximum value, and then it drops off from this maximum value. And this is the general shape that we'll see in our experiments, as we'll see later. Okay. Here I'm going to introduce a concept called impact. This is the graph of a representation of the graph of a velocity field without the cup, the bottle there. And then this is the velocity field with the bottle. When we divide the area of B divided by A, you get the impact of the bottle. This is basically comparing the average velocities of the two bottles. And we use 1 minus B divided by A to get an impact, where 0 is no impact and 1 is very big impact. 1 would basically mean a completely flat velocity field. So experimentation. The first thing we tried to determine was when the candle will blow out. So we determined that at a certain velocity of air, the candle will be blown out. And for our candle, the specific velocity is 0.4 meters per second. Due to the time dependency of the velocity field, the candle may actually be blown out at random moments. Look at the video here. The candle flickers, and eventually it actually blows out. Oh, it's taking a long time. So the second part of the experimentation is that we put the bottle at various distance from the fan so that the velocity of the hitting the bottle is different. And then we measured the velocities, the air velocity field after the fan. We used an anemometer to do this. And we used this system in order to center the fan to the anemometer to the fan, and also to center the bottle, because you can slide that. The experimental shape of the velocity field looks like this, and it reaches a maximum, and then it drops down, just like predicted in the CFD simulation. So this is a quantitative analysis. The impact of the bottle doesn't really look that good. That's because the system is actually turbulent, as discussed before. But as you can see, when the velocity increases, there's a trend where the impact of the bottle actually increases. So when the flow of air is very fast, the impact of the bottle on the velocity field actually increases. So the third experiment that we did was the shape of the bottle versus the position of the maximum air velocity. As you can see here, we were generally unable to see a trend here with the max, comparing the volume with the maximum location. These are all cylinders. We were unable to actually see a trend, and this is because the predictability due to high turbulence flow. Also, the time dependency of turbulence actually causes error to be very large, as you can see there. From observations in the experimentation, sometimes, in very specific instances, the velocity field can actually fluctuate so big that there's a 1 meter per second, 0.7 meters per second fluctuation in the amplitude. Conclusion is that the Kawanda effect can be demonstrated through a computer fluid dynamic simulation. The system is turbulent and time dependent. The candle blows out at a certain air velocity threshold, and the average air velocity behind the ball or increase to a maximum before dropping out. The bottle is more inconspicuous, as described by the Thompson when the velocity of the air is slower. This means that when the velocity of the air is slower, the change in the velocity of the velocity field behind the bottle is less than if the velocity field is fast. This makes sense because the higher the velocity, the more vortices there are. And the more vortices there are, the more turbulence there are. Turbulence does not contribute to a forward velocity, and therefore more energy can be dissipated. In this case, therefore, your bottle, the velocity going forward would be less energy is lost if your velocity is slower. Okay. The last point is that the maximum velocity is highly unpredictable, as you can see in this graph here. Oh, oops. You can see in this graph here. Okay. To add on, the program used in question is called FreeCAD, and in modeling this simulation, the boundary conditions uses for the top three sides and the side to the very end, we used an open boundary condition, which means that the air will not be impeded by the boundary. It will flow out, basically an outlet, kind of. The inlet here, this is the boundary condition here is the inlet, and then there are wall boundary conditions for this face, the bottom face, and the cylinder that's inside, as well as the cylinder's top. And when we run the simulation, we'll see that the flow will be able to visualize things like these. So this is a more in-depth view of the simulation at hand. Also, the Reynolds number was calculated not by the CFD for clarification. The Reynolds number was calculated by using the Reynolds number formula and assuming the diameter of the bottle as the
Excuse me, time's up. Questions from opponent, you got 2 minutes.
So, first of all, I want to ask about did you measure your Reynolds number during your experiment?
Reynolds number cannot be measured.
Oh, sorry. Did you calculate your Reynolds number during your experiment?
No, I calculated it before. I have. Okay, we'll go back.
So you didn't?
Yes, I did. I did it beforehand.
And what is the range of the Reynolds number in your experiment?
What?
What is the Reynolds number, the range of the Reynolds number in your experiment?
It is always greater than 5 times 10 to the third power. It is always greater.
Can you repeat
It is always greater than 5 times 10 to the third power.
So you cannot give me a exact number.
No, I'm saying that it is always greater than 5 times 10 to the third. Therefore,
okay,
it is.
So there's no exact number.
No.
Thank you.
Okay.
And did you consider the vertical height when you're doing doing your simulation? Because the airflow is not parallel to the surface. With the surface in the bottom, which is like the gate or something.
No. However, I see your point because the vertical height does cause turbulence as well. We did not account for that.
And in your theory page, you show that there is vortex.
Yes.
I'm curious that is there vortex that you see in your experiment or your simulation?
The vortices actually you can't really see in your
So
in
you
real life.
cannot observe it, but
We
you
have
put
not
it
been
in
able
the theory
to.
page.
We have not been able to observe it yet. Yeah. It requires maybe smoke to observe, but we didn't have that.
Okay, so did you discuss about vortex during the speech?
Yeah.
Yes, but you didn't find vortex, but you discussed about vortex.
Yes.
Okay, and did you ask about what in your experiment the velocity field will change with time, right?
Yeah.
So when you're doing your experiment, how can you measure with velocity field, or you
I averaged it.
I'm sorry,
I averaged it.
you averaged it.
Yes.
Okay, so can you make
Excuse
sure?
me, time's up.
Thank you.
Opponent, you've got 3 minutes to prepare for the next stage. Chance will take the floor for up to 4 minutes, followed with discussion with reporter.
Thank you. Honorable juries and our competitors and the opponents from Team Excelsior. And today I'm going to oppose the problem number 2, inconspicuous bottle. The problem statement said that put the lit candle behind the bottle. If you blow on the bottle from the opposite side, the candle may go out after the bottle was not there at all. Explain the phenomenon. And I think the main focus should be why the candle is blown out, and why the airflow can bypass the bottle, how the characteristic and the airflow velocity will affect the attachment. In my points, I think the structural solving problem is first we have to discuss why the airflow can bypass the bottle, which can be explained by Coulomb effect. And secondly, I want to investigate how the properties of the bottle and the airflow will affect the velocity distribution, because this can help us to understand how the bottle was bypassed by the airflow and how the airflow can extinguish the fire. And in this part, I think the two main parameters should be the Reynolds number and the diameter of the bottle. And then at last, I think the discussion about boundary condition for the candle to go up will be very important, because the problem statement asks us to extinguish the fire, and the boundary condition for reject requirements is important. So I think they can be explained by transmission efficiency of the airflow velocity and also the distance from the bottle. And this is a strong and weak point I think about the reporter. At the strong point, he gave that phenomenological explanation about Coulomb effects, and he also demonstrates simulation of the program. But I think the reporter didn't do a good job on experiments, because they give theoretical simulation. But in their theory, they say that there will be vortex. But in my opinion, vortex will not create as the Reynolds number when it is bigger than, I think, about 10,000. And actually, in the airflow, if the Reynolds number is lower than 10,000, it cannot bypass the bottle. It cannot extinguish the fire, in my opinion. So I don't think that it can fit with the phenomenon. And also, as I say that the vortex, the Reynolds number should be wrong in their simulation, so it cannot explain the phenomenon. And also, they didn't calculate the exact Reynolds number, which cannot help them to understand the kind of airflow in their experiments. And they also have that connection between the phenomenon and the result, because they only said about the ring distribution around it, but didn't say about how that will affect the extinguish of the fire. And also, they didn't explain the error occurred in results. They only say that it will be affected. And they didn't say about deviation between the theory and experimental data. And also, they didn't discuss about upstream velocity, which caused the lack of barometer density. And this is the point I think has to be got during in experiments. So about the Coulomb effect, they didn't discuss about pressure distribution, but I think it's important because it will cause the entrancement of the airflow, which is a part of Coulomb effect. And also the vortex thing, I want to be clarified about it. And also about the setup, I think the nozzle will cause a divergence, and the size of it will also affect the airflow. And the infinite flows and continuous flows should be discussed too. And in this part, I think the properties of the bottle, which is diameter, they discuss about it, but I think I want to clarify it by discussing more about separation angle, which will affect the separation region around behind the bottle. And the shape also will affect the drag coefficient and the kind of airflow, so I think that will be important. And certainly the Reynolds number, they didn't calculate about this, but we also can discuss about how it will affect the separation and the turbulence flow. The Reynolds number will change if they have a vortex or not. And certainly I will talk about boundary condition, which I think is mostly important, because this will talk about how will the candle be blown out by the bottle. And we're discussing three main parts, which is upstream velocity, which will affect the Reynolds number and diameter and the distance between the bottle and the candle.
All right, proceed to discussion.
Okay, so first I want to ask about that. Did you have anything about the pressure distribution in your experiments or in your simulation?
How do you measure pressure? How would you recommend me measure pressure?
So we cannot measure pressure, but I think the pressure distribution can also be guided as the difference between Reynolds number and the drag coefficient. Because the pressure distribution around it may cause the drag coefficient to be upward and create more drag force, which will affect the phenomenon. Okay, so are you trying to write Bernoulli's principle?
Yeah, in general, if you want to get the pressures, you know the velocity is more than pressure.
But that will also, the Bernoulli's equation is fully as this.
Where's your surface?
But in your experiments, what?
Gravity is negligible. Where's your surface in the surface?
But in your experiment, your airflow has a vertical distance with the airflow. It's like this. This is the airflow, and this is the bottle, and these are the wings. So there will be a height difference in your experiment. So I think this should be considered too.
But you look at rho is L. This is from here to here. It's not that big.
So you didn't show that in your
The pressure is. How do I show that?
Sorry, in your simulation. So.
How do I show that myself?
Okay, okay, I think we can pass this part. Okay, and also, how do you think this will affect the entrancement of the airflow? Because in Corona effect includes that the airflow will fluid around the curved bodies, and also it will entrance the fluid from the surroundings. So it has two main parts, and you only discussed about one. And how do you think this will affect the entrancement of the airflow?
So, this is sorry.
Yeah, it's
So,
okay. It's okay.
so your air will go like this, right?
Yeah.
Then
Yes. Yes.
this is your bottom here. So basically your air will look something like that, right?
Yeah, but why will the airflow flow like this in this parts of the region? Why will it entrance or force to curve it like this? Sorry. Okay, so I think.
Because the pressure jet creates a low pressure area and therefore it catches everything.
So you think it's the low pressure, the asymmetric low pressure around the jet flow will occur the entrancement of the airflow?
Yes.
Yes. Okay. So I think that's clarified about the entrancement.
Okay.
And also, I want to do the next part about how the vortex will affect your phenomenon, because you mentioned vortex in your experiment. So in this part, you can see that he has. Oh, sorry. Can you skip the last page with the with the theory page?
Which one?
The theory page with a lot of papers. Sorry. Not that one. Okay, so in the picture you have a lot of the airflow and there's a vortex here, right?
Oh, that one. Okay.
Yeah. And why do you think this vortex will happen?
This one?
No, it's your theory page. Oh, it's okay, but there's a vortex in here, and how do you think this will affect your phenomenon?
There's a vortex where?
Under the jet flow in your theory page with 5 pictures.
My theory page is like.
Yes, just download in Wikipedia.
This one?
The Corona effect part.
Oh, that one.
Well, I think the vortex.
So this one, right?
Yes. And how do you think the vortex will affect the phenomenon?
This is only when there's a gap here, right?
Yeah.
Okay, so this is a gap of low pressure, right?
Yeah.
Okay, so
But how will
this is a gap of low pressure as well. So this will be turbulent.
Yes.
Here. But since this is close to my fan is actually very close to the
Yes. Okay.
floor, so it won't be turbulent.
But I think that there will not be a vortex. Actually, I don't think there will be any vortex.
Whoa, just look at that.
Yeah, I know, but it is determined in Reynolds number. And actually, when human flow anything is kind of between the wind velocity is between the region of like 4 meters per second to 18 meters per second.
You know that
10 meters per second.
kinematic viscosity of air is 1.85
Yeah, I know.
10 to the negative.
Mu. Yeah, mu.
I don't know how to write that.
So no matters. Okay, and yeah, because that of
The Reynolds number is equal to u.
yeah, I know what is Reynolds number.
Okay, yeah. So if your kinematic viscosity is very small, then obviously your Reynolds number is going to be huge.
Yeah, and the
So
Reynolds
most
number.
of the things in the air is turbulent.
Actually, turbulence didn't equal to vortex because in our experiment, behind the in your experiment, behind the cylinder, there will only be vortex around I think the Reynolds number is around 10 or something like that. And this is about your theory, right?
So it has to
Yeah, but when human spreads, it's almost like in my calculation, I think it's about 10,000 or 10,000 to 180,000. So in that part, there will not be vortex. There will be turbulence flow like this, and there will not be vortex.
Okay, so maybe I think a helpful thing to do is actually just calculate the Reynolds number.
Yeah, the Reynolds number.
Reynolds number.
Sorry, I think I did the calculation on Reynolds number. I think.
No, I think we should do it together.
No, I don't think it's about calculation. That's kind of a math question. So I would
No,
say
I calculated the minimum Reynolds number at 0.4 meters per second was 10 to the was 5 times 10 to the third.
Yeah, but that is the
That's the minimum.
Yeah, that's the minimum number
That's
to,
the minimum
to
number.
sorry, to extinguish the flame.
Yeah,
But as you are bypassing the bottle, the velocity will decrease. So at this part, which is where the wind source is, it will be bigger than 0.4.
yeah. So at this point it's turbulent, right? Do you agree with me?
Yeah, the whole thing is turbulent, but turbulence didn't equals to vortex.
Then what's turbulence equal to?
Turbulence means turbulence actually.
Turbulence
It just
means
that.
vortices and eddies, the energy associated with vortices and energy.
In my opinion, I think the turbulence is the meaning of turbulence
that's
is without. Sorry.
That's the definition of turbulence, the energy associated with eddies and vortices. Like, how can you
It's
say that there's no eddies and vortices in the turbulence?
Sorry, there will be. Okay, so obviously, I think we don't have a disagreement, so we'll just move on. And in your
Totally have a disagreement. Okay, sure.
yeah, so in the setup, you use a fan to produce the wind. But if you blow your mouth is the size of this, and the fan is not the size of this. So how do you think the size will affect the wind blow?
You blow air, but one effect.
Yeah, and
air from the side will
but
go out, and then the drip will actually expand. So,
yeah, but
so
I
this
want
will
to ask about how the diameter of the nozzle will affect.
the diameter of the nozzle,
Yeah, or the fan, the wind source.
how would that affect what?
Affects if you can blow off the candle.
So if your diameter is big, if your diameter is big, then it'll be easier.
So you cannot just enter stores about this question. Yeah. So do you think that if the wind source is bigger, it will be easier to bypass? So it didn't fit with the phenomenon because your setup is big and it's easier to bypass the bottle than the blow that the statement and manual about.
The recommendation is for me to simulate with a smaller nozzle.
Yeah, but simulation cannot fit. It doesn't actually fit with your experiment, right?
Okay, I agree
Yeah,
with that.
and I would like to see the boundary condition part. How do you think? You didn't do a nozzle. You did the diameter as the parameter, right? In your experiment.
Okay, yeah.
Yeah, and how do you think that will affect the boundary condition to blow up the candle?
What's boundary condition? What's your definition?
I mean, if it's under the diameter is bigger or something, you cannot blow off the candle.
You know, boundary condition means a lot of things.
Yeah, I say that. If in a boundary condition, if your diameter is bigger than the boundary condition, you cannot blow off the candle or in a kind of.
Do me a simple favor. Define boundary condition.
Yeah. So in my explanation, I think the boundary condition will change because the diameter will increase. It will decrease the transmission efficiency of the airflow. So in my opinion, when diameter is bigger, the boundary condition of upstream velocity to blow off the candle will be bigger because the transmission efficiency will be decreased.
Okay, can I clarify? Your boundary condition means the minimum velocity to blow the candle.
Yes, I think
Oh,
so.
okay. So you're saying
Of the
that
upstream velocity.
you're saying that if the upstream velocity is higher than the boundary condition, what do you have?
But no, I think
Excuse
the
me?
diameter. is
Time's
bigger.
up. Opponent, you got 1 minute to summarize your discussion.
So, and during the discussion, we discussed about the pressure distribution and how it will cause the entrancement. And we discussed that about the entrancement because of the low pressure across the airflow, it will entrance the fluid from the surroundings. And also, we talked about vortex. I think that vortex will not be implied in this phenomenon because the Reynolds number to produce vortex is too small, and so it will not fit with the phenomenon. And also with the setup parts, I think the reporter did a not so accurate job as to choosing the fan as the nozzle, because as you're using the fan, it will be bigger, too much bigger than our mouse, so it doesn't fit with the theory, which doesn't fit with the phenomenal statements, which means that you have to blow. And also about the Reynolds number that we consider out, I think the turbulence flow didn't equal to vortex, because some of the turbulence flow won't cause vortex, but some flows, turbulence flows. And also about the boundary condition part, we talk about diameter. And I think with bigger diameter, okay, thank you.
Questions from reviewer? I've got 3 minutes.
So, question for the reporter, can you show me that in your specifically your programming, which is the solution with
Program, okay. So I use a program online called SimScale in order to do the CFD.
So that rectangular box, what is that?
So imagine this is the area where we want to simulate. So, oh, I need to draw that.
It's okay.
Oh,
Okay, so at page 21, you mentioned about that the VC, which is like the smallest velocity that can kind of flow out.
Yeah.
So what is the condition of the distance and the diameters of the hole?
So I think the condition of the candle blowing out is the velocity field above the candle must have an average of 0.4 meters per second.
Okay, so before that you kept mentioning about Reynolds number,
Yes.
and you mentioned that you think that in your observation that the Reynolds number is always larger than the 10 power 4.
5 times 10 to the power.
Okay, so how did you measure the Reynolds number?
Reynolds number is not measured; it is always calculated.
And some questions to the opponent that so do you think what parameters are important when discussing about this issue?
I think the upstream velocity and also the diameter of the bottle.
Okay, and also a component and you are discussing about the vortex and you're using the Bernoulli's principle to find the relationship. And I was asking that, do you think that Bernoulli's principle is suitable in this case?
I think Bernoulli principle can tell us about the trend that it will become bigger, but it cannot use to be calculated because Bernoulli principle states it's an inviscid fluid, but the fluid is not inviscid.
Yeah, absolutely not. The velocity field behind the bottle cannot be predicted by Bernoulli's at all. But however, if you don't have a bottle, the Bernoulli's principle does a great job.
I'm sorry, I don't agree with it, but it's okay.
Okay, and after that you are discussing about the parameters, do you think that the ratio of the diameters of the ball and the wind flow and the wind with and the place wind flow out, with the ratio of that affects
That means the ratio of the size.
yeah, the size of
Yes,
the
I
boat.
think absolutely.
Okay. And if you just discussing that you use the Bernoulli's principle, do you think that the height of the wind flows out?
Excuse me, time's up.
Okay.
Review, you've got 2 minutes to prepare for your review. Press start now?
Yeah, sure.
Okay, all right, you may begin.
Okay, so our majority fellow debaters, this is the Team just speaking. Okay, and this is our reviewing. Okay, so the problem statement I believe that we have all seen before. Okay, to put a lid handle is behind the bottle, and when it blow from the opposite side, then it can go out. So explain the phenomenon. And I'm going to make a short outline of what the reporter just reported. And start from the observations. I think the observation video is quite clear. And but on the other hand, that the observation, I think the amount is a little bit too much. And about the theory part, the reporter used the clear diagram to describe the phenomenon, but however the cons that about the k omega effect, that I think there's too many complicated formulas, and it doesn't appear in the later up slides. And for a setup part, the reporter lists a lot of programs used. Okay, and on the other hand, that I think there's a little too much emphasis on the programs. Yeah, and it will cause a little bit of trouble. And so for the experiment part, that the good part is the reporter used video to make their experiment to be clear. And for the conclusion, and they introduce some of the source of the errors, which I think is quite good. But on the other hand, that there's some I think they are too complicated, and furthermore, they did not clearly define the height of the twin together. Yeah, and also in the later on slides, they barely mentioned in the quanta how did this quanta affects their experiment. Okay, so this is for the opponents, the pros and cons, and the good parts I think they really like fully graph the flaws and reporters and the reporter's experiment. Okay, and they can also she can also came up with her own idea. But the cons, I think on the PowerPoints there are too much words, and I think the speed was a little bit fast to understand. Okay, and about the clash between the opponent and reporter, and the opponent first thought she believes that the radius number is too small, so I think there will be no vortex. But the reporter says that he believes that there is. In my perspective, I think that the reporter and opponent came up with clashing results, but the opponent did not reveal where the results come from. Okay, and for the next part, opponent believes that maybe they use the Bernoulli's principle to explain the phenomenon, and the reporter believes it does not. So, what I think is that the Bernoulli's effect may not really affect the results. And for another clash is that the opponent wonders how the vortex will affect the phenomenon, and the reporter says that he believes that vortex is close to the ground and does not affect the flow very much. And I think that the reviewers cannot quite come to. I think I can't quite come to a conclusion because the opponent claimed that there's a vortex happening where that was impossible, which is contradictory. Yeah. And our part is the height difference may cause a Bernoulli's effect. And reporter replies that some things they cannot quantify. And which I think is the report is give a pretty unclear answer, and they even try to explain more clearly. And in my perspective, that what the different surfaces of temperature, like my questions are, what different surfaces of temperature affect the phenomena, and also is that reporters simultaneously change height and diameters of the bottle. Would that affect the results? Yes.
Time's up. Before that, you got 2 minutes to make a concluding remark. You guys use projector?
Quanta effect. So in summary, the quanta effect was assumed throughout the presentation. So the opponent, the reviewers claim that I didn't use quanta effect is, I think, a bit unjust. Bernoulli's principle cannot describe this. This is a complicated turbulent system, and it's also very, very complex. The Reynolds number is, we calculated, is 5 times 10 to the third, and therefore the existence of vertices is very it's very evident. The setup, I agree with the opponent that maybe in my simulation I should have made the nozzle a bit smaller, and I think the opponents were giving me this advice. The boundary condition, I don't think it matters. What matters is the average velocity over the candle, as I mentioned. And that concludes my summary.
Right, you done?
Yes, thank
Okay,
you.
good. Come to questions from jury member. Any questions?
Remember you mentioned about equipment, like to measure the speed of the flow for the anemometer? I just wondered whether that measurement will affect the real speed, because of the size of your airflow and equipment. I don't know how large the equipment is.
Oh,
Will that affect the result? We put in the measurements before,
you mean the computer fluid dynamics? Or,
no, by measuring the results of the speed.
so the
Will that reflect the real value?
that reflect the real value.
The equipment itself, once you insert that equipment into the, the path of the flow, will that affect the speed?
I think it actually could affect the flow of the
If
velocity.
we are talking about a huge area, then sure, there's negligence effect, right? But since the one you show us is kind of small area, so I just wonder, will that affect the measurements?
I think it could affect the measurements, but I don't really have a way to account for it. So I'm not really sure what to actually do about it. I'm not sure if it's possible to account for it. If it is, then I would want to do more experiments to account for it. But I really do not know how to do it.
Any more questions? I have a question for three of you. If I change the cross-section of the bottle from a disc into an ellipsis for you, how does that affect your results?
Well, I think if the long and it's the long part that is facing it will be harder for the airflow to bypass the bottle, and if it's the short part that's facing the airflow, because the separation location will be moving backwards, and that will cause the airflow easier to bypass the bottle.
I think if we change the shape of the bottle, then we change like a rectangle, and then when the wind like go pass by, and then I think it would separate like more obviously in the beginning. So if the wind is separated more, if the wind is separated in the beginning, then maybe it's difficult to go back together and to make the
Order?
So my opinion is that the ellipse is actually a more aerodynamic shape, and I think that the impact, as I introduced that concept, the impact of the ellipse will actually be less than this. The impact of the ellipse will be less than this.
Any other questions? I got a question for the opponent.
Yes.
At one point you were talking about the low GH,
Yes.
all right?
Yes.
How important is this term?
Well, because in the opponent simulation, it didn't mention that how high is the airflow, and if the height is very high, then it might affect that. What is the direction of the airflow? Because I don't know if the airflow is flowing this side and this side, and will that affect?
Are you able to estimate how, relative to the P naught, how much it's going to be, doing, if you think of this P naught
Yes.
and this low GH,
Yes.
what would be the low GH in terms of P naught?
Well, I think that if the height is high, so that number is big.
But in the real case, I mean, just a, bottle, which is probably 40 centimeter high.
I think that will not affect very much, but that will cause the measurements of the wind field and the reporters' experiments became very inaccurate.
Right?
Okay, I think we already have a mention about the temperature, right? Temperature, right?
Yes.
Yep. So how do you expect the temperature will
Maybe
affect the
go
result?
back to the velocity. Of course, I mean that when you first come out from machines, that the velocity remains the same. But I think the temperature will like affects its like affects the air atom inside some energy. So maybe it would affect this velocity.
So the effects of temperature is actually that it decreases the kinematic viscosity of the fluid. So therefore, the system will actually be more turbulent if the temperature is reduced. So it will have more turbulence in the system.
Apollo, you want to say something?
And I think that the temperature might affect the airflow, but if the temperature is around the candle and you know that the hot air will move upwards, and if that's only if the upstream velocity is bigger than the velocity of the airflow moving upwards, then I don't think that will affect much in the phenomenon.
All right, so come to the grading time. Remember city figures. Okay. All right, pretty sure your score. Start from me. 6. Oh, for reporter, yes. I'm sorry. Yeah. Start from me for reporter. 6, 7, 8, 6, 6, and 6. Score for opponent. Right, raise your score. Start from me. 9, 8, 8, 8, 8, and 7.
Thank you.
Score for reviewer. Please raise your score. 7, 9, 7, 8, 6, and 6. Okay, want to say something? See why?
Well, I think they did a good job on songwriting, very interesting work. And they did a good job on songwriting, performance, argument.
All right.
I think they did a very good job on listening to the
Yeah.
team.
All right, thank you. So let's take a 10 minutes break. Thank you. 오, 시승은做的。
墙上才是电风扇。
这个是电风扇，弱的就好。
那个有点吵。
我是开前面的话，头一定会动，所以
可以吗？
但这个时间点，
你在
明天有人来，明天就是
月底。
对呀。
Oops.你们刚刚测试有这个问题吗？That's fine.
Yeah.
Well, listen. Alright, okay, so let's start second round. Opponent, you got 1 minute to challenge the opponent for the problem. The problems are on the slide.
We challenge
Challenge problem 14, forming power.
Problem 14 is challenge. Opponent, you got 1 minute to make a decision. Problem rejected, back to opponent. You got another 1 minute.
Challenge problem 13, fishing.
Problem 13 is challenge. So that one is not available? Number 13.
It's available for this.
Is it available? Is it available?
Problem 13, right?
Yeah,
It's okay for this time.
it's available, right? Yeah, I'm sorry, it's available. So you check it once, or what? You accept it? Okay, problem accepted. So we've already got 5 minutes to prepare for your report. Oh yeah, write down your representative's name on the block, please.
关掉我不会开暗吗？
风扇，关掉好。如果到后面这边不会。
关掉。那就飞来飞去。哦，那个是这个而已。这个。
就是这边的角色是看看现在这个，就是你现在这个局，如果你不是我的话，还有谁要为这个角色就是好看
Eric He goes by Eric. He goes in general. Yeah.
所以没有了。You change member, right? 被改。You change 下午
对对对，所以他们应该不能再。
你就不过算。不过。对啊，这个更多走光了。早上也是。主席要注意他们有。Alright, so they have changed members. Here. It's 那个 member 可以换吗？
这是新加坡的号。
No.
It's the old list.
This is correct.
So you were here earlier, right?
Yeah.
Then that's it. All right. So report on your turn. English start.
Hello everyone, I'm from Think Excelsior. Today I'm going to talk about problem statement number friction oscillator. This is the problem statement. A massive object is placed onto two identical parallel horizontal cylinders. The two cylinders each rotate with the same angular velocity but in different directions. Investigate how the motion of the object on the cylinders depends on real parameters. And from this problem statement, we think we should main focus on the force analysis of the massive object. And the motion depends on the real parameters. And this is my outline. First of all, I'll talk about my preliminary experiments, including the observation videos, as well as the distinguishing the differences between the outward and towards rotation of the cylinders that will work on the massive object. And second, I'll talk about my physical model, including the force analysis of a massive object and a simple harmonic motion. And third, I'll talk about my parameters. We will change the initial displacement of the very center of the rod, and we will change the material of the rod, which is the friction coefficient. And we will change the length between two cylinders. And at last, I'll talk about my conclusion. And as we observed, if the rod is placed at the center of two cylinders initially, then no matter the rotation is outwards or towards, then it will remain static equilibrium. And as we observed that if the initial displacement is not at the center of two cylinders, then if the rotation is outwards, then the rod will accelerate in one direction. And if the rotation is towards, then the rod will oscillate. So from here we can know that the condition of the oscillate is that the very center of the rod will not place at the center of two cylinders initially, and the rotation must be towards. And this is our observation video. And at the video you can see that as soon as we put the rod at the cylinders, and it will start to accelerate immediately. And in the right video you can see that the rod, the rod is oscillating stably and continuously. And this is the trajectory of the very center of the rod. In the left chart you can see that if the rotation is outwards, then the displacement will increase exponentially. And in the right chart you can see that the oscillation of the very center is stably and continuously. And we can see that no matter the amplitude or the time of each period are similar, so we guess that it is nearly as the simple harmonic motion. And this is our theory. We assume that the rod is placed at the right side of the center of two cylinders. So due to the torque, the normal force of the right cylinder to the rod will be bigger than the normal force of the left cylinder to the rod. So the friction will be bigger. The right cylinders to the rod will be bigger than the left cylinders. so that the resultant force as well as the motion will go to the left in this moment. And if the rod is at the center of two cylinders, although the normal force are the same, but due to the inertia, it will keep going to left. And if the rod is placed at the extreme left, and the situation will just be the same as the rod is at the right side that I have explained. And from the torque, we can get the result of the two normal force. And from the result of the normal force, we can get that the resultant force will be this equation. And from this equation, we can find out that the resultant force is proportional to the displacement. So we can show that it is simple harmonic motion vertically. And from simple harmonic motion, we can get the equation of motion as well as the time of each period will be like this. And this is the equipment we use in our experiment. First of all, we use the tube to be the cylinders, and the rod will be the massive object, according to the problem statement. And we use the controlling panel to control the motor, and we use the motor to activate the cylinders. And as soon as the cylinders goes on the terminal velocity, then we will put a rod on the cylinders and do our experiments. And this is the actual setup. And these are the parameters we changed in our experiment. First of all, we changed the initial displacement of the very center. And we changed the materials, which is the friction coefficient of the rod and the length between two cylinders from the equation of the simple harmonic motion previously we get. And in the first experiment, we can see that we changed the initial displacement of the very center of the rod. And the weight of the rod we control as 16.5 grams. And the distance between two cylinders will be 25 centimeters. And the angular velocity will be 200 RPM, and the rotation will be towards. And from the equation of simple harmonic motion, we can see that the amplitude will be same as the initial displacement. And in our experiment, we can see that the initial displacement will also nearly same as the amplitude. So both from our experiment and the theory shows that the initial displacement will be nearly same as the amplitude. And before doing our second experiment, we should measure the friction coefficient of each materials. And the method that we measure is to use the same material of the cylinders to be the slide. And the angle between the table is about 45 degrees. And we will put the piece of materials on the top, and we will let it slide down. And we will calculate the time of sliding down and use the result as well as the equation we get to find out the friction coefficient of each material. And these are the results that we measured. And this is our second experiment. We changed the friction coefficient which is the materials of the rod, and we also control the weight of the rod, distance between two cylinders, and the angular velocity, and the rotation will be towards. And from the equation previous, we get that the friction coefficient will be proportional to the resultant force. That means that the time of the resultant force affecting on the rod at the same unit of distance will decrease. And from our experiment, we can see that as the frequency of the friction coefficient increase, the time of each period will decrease. And from the formula of the simple harmonic motion, we can see that the period of time will be negative proportional to the root of the friction coefficient. So both the experiment and the theory shows that as the friction coefficient increases, the time of each period will decrease. And the third experiment, we changed the length between two cylinders. And we also control the weight of the rod, and the material we choose to use the plastic, which friction coefficient is about 0.3. And the angular velocity will be also 200 RPM. And as the equation previously gets that, as we know, that if the length between two cylinders increase, the resultant force will decrease, which means that the time of the resultant force effect on the rod at the same unit of distance will increase. And in the experiment we did that the length between two cylinders will be the positive correlation with the time of each period. And in the equation we get from the simple harmonic motion, we found out that the period of time will be proportional to the root of the length between two cylinders. So both our experiment and the theory shows that as the length between two cylinders increase, the period of time will increase too. And this is our discussion. As we know that if we integrate the force over the displacement, it will equal to the force. It will equal to the work. And if the x-axis means the displacement and the y-axis represent the force, then the area will represent the force that has done for distance. And the force 1 and force 2 will be the relations of the two cylinders affecting the rod. And so the area 1 will represent the energy that the resultant force has done to the rod at the first half of displacement. And vertically, the area 1 will be same as the area 2. But actually, there is damping existed. So basically, the energy will be absorbed by the resistance. So actually, the area 1 will be less than area 2, which means that the motion actually it will decay, and eventually it will be the very center will be stay at the center of two cylinders, and it will remain static equilibrium. And this is our conclusion. As we observe, if the rod is placed at the center of two cylinders, no matter the rotation is outwards or towards, it will all remain static equilibrium. And if the rod is not placed at the center of two cylinders, and if the rotation is outwards, then the rod will accelerate in one direction. And the condition of the rod oscillating is that the initial displacement of the very center of the rod will not be at the center of two cylinders, and the rotation of the cylinder should be towards. And this is our theory. We see that due to the torque, the normal force of the right cylinders will be bigger than the left cylinder to the rod. So the resultant force goes to the left. And so that the motion of the object will go to the left too. And if the normal force, even the rod is placed at the center of two cylinders, due to the inertia, it will keep going to the left. And from the theoretical derivation, we can get that the force will be proportional to the displacement. So vertically, it is simple harmonic motion. And from simple harmonic motion, we can get that the equation of motion as well as the time of each period. And basically, in our experiment, we did observe that it is a damping motion, but we basically choose the first few oscillations to be the experimental data, so that you can see that the experimental data is nearly fits to the theory. And in the first experiment, we changed the very center of the rod, and as we know that the initial displacement will be nearly same as the amplitude. And in the second and third experiment, we changed the friction coefficient as well as the distance between two cylinders. And as the formula previously gets, that if the friction coefficient increase, the resultant force will increase, so that the time of the resultant force effect on the rod at the same unit of distance will increase, so that if the friction coefficient increase, that the period of time will decrease. And from formula we get that if the distance between two cylinders increase, the resultant force will decrease, so that the time of the resultant force effect on the rod at the same unit of distance will increase, so that from our experiment we can show that as the distance between two cylinders increase, the period of time will decrease. This is the end of the report. Thank you for listening.
All right, thank you. Questions from opponent? You got 2 minutes?
What's the name of your method?
That the object
Very long or very
no, that the motion will not be, the rod will not be bumped up, and the weight will not affect the rotation of the cylinders. We define the massive object as this.
Will the rod jump up, jump like
if the rotation is very fast, and we observed it will. So we didn't make the rotation of the cylinder so fast, like that.
Are you sure the velocity of the two motor will be same?
Yeah, because we use a controlling panel. And the control panel will be the
Can you
control the
can
speed.
you repeat the painting?
Daniel.
Yeah.
Thanks. Okay. Okay, sorry.
Hold on, you may carry on. Another questions?
In this.
No, that's fine. Back to opponent.
Okay, and the area one will be represent the energy that the resultant force has done for distance at the first half of the statement. And vertically, the area one will be same as area two. So,
Okay.
but actually there are.
I think that's enough, yeah.
So
Back to
I'm
opponent.
sure the rod will be the SHM.
Vertically it will, but actually it won't. But the observation, the trajectory is the perfect one that we have. Yeah, it's a perfect one. So it seems that it is simple.
Right, so you got 3 minutes to prepare for the next stage. Right, all right, you will take the floor for up to 4 minutes. Proceed to discussion with
Hello, Jerry and fellow debaters. This is Antonian from Team 电到下下告 Where is our current matter? A massive object is placed onto identical parallel horizontal cylinders. The two cylinders each rotate with the same angular velocity, but in opposite directions. Investigate how the motion of the object on the cylinders depends on the elevation parameter. Within the key point is the massive and same angular velocity. And upside directions. Previously, there are some pros and cons. Program 7 observation. The video, it has a clear video and a correct review. Theory involved. The code is using animation to build the model and easy to quantify the phenomenon. But it has cons. First, it's too hard. The math is too hard, and the theory details aren't all clear. Variable setting and theory may have too many problems to prove it in the real environment. Experience and results. Carefully analyze meaningful data and discussion on all suitable for the theory. Set up does not correlate the problem statement. And within maybe having done consider a larger possibility and no energy. Conclusion. It has clear presentation and it's easy to understand the theory. And the theory makes the phenomenon picture. Some counts simply restate the experiments and observation, does not have a real conclusion. And they can do more factors discussion. Okay, all discussion.
We're going to proceed to discussion?
Yes.
Okay.
How do you make sure the table is flat and the device doesn't wobble when it functions?
We have checked by the balance horizontal. Yeah. With that, we have checked the table is flat and the device is flat and it will be parallel to the road.
Do you have the experience that the table is not flat?
Oh, you mean we observe that it will if it is like left and the very center will mostly approach to the left. But I think it is not the main it is not the main point that the problem statement asks us to give.
The amplitude will change.
I don't know. We didn't. We have. I think it won't.
You won't. Okay. Are you sure the motion will always the negative friction, or it will be the static friction?
Mainly, the cause of the oscillation is because of the kinetic friction, and it might have a very small observed time. We cannot, but because we think that the static friction occurs very limited of time, because as we know that.
So you say you have the static friction,
but I think it doesn't affect the experiment a lot.
So you doesn't think the static friction will affect the amplitude or the period?
It is remain as same velocity of the cylinder, it won't.
Okay. Can you tell me what you mean with
the amplitude was K, and eventually the motion will nearly remain static or different.
Did you change the angular velocity of the motor?
We have changed it. And in this experiment, we changed the angular velocity of the cylinders. And as you can see that if the angular velocity is very low, the inaccuracy is more big. And I'm curiously that it is. Oh, sorry. I want as we observe, it is not really oscillation. It is not periodical, and we didn't think that it is the actual experimental data.
What thing do you use as a way to present a motor speed?
We use there is a digital number of the control time, so we can know that the motor speed. It is RPM. The unit is RPM. And we use the 45 degrees to measure the friction coefficient. Is that
so your amplitude will not change by the time.
by the time?
With the time.
Yeah. The amplitude goes.
Are you sure?
And
You said
and the angular
that
velocity
you have a
of the
static friction.
but it
your
is
moment.
happened in a very short of time because as we know that it has, but it doesn't affect a lot of the experiments. So basically we cannot observe it. And okay.
Did you use certain degrees to measure the coefficient?
Because tangent theta will be if the theta is 45 degrees, then this will be 1, and this will be square root of 2 divided. Yes, divided by 1. Yeah. So it is good. It is more efficient to measure and calculate.
The massive is very long. It's long.
It's long.
Your mass is long. Have you changed maybe and
If we have placed the motor, that if we
we said I said the rod.
the rod might affect the stability of the motor because there is the maximum amount of the maximum work of the controlling panel as well as the motor. So we cannot put the very massive rod. That basically, if the work of the motor is powerful enough to carry the rod, it will have the same. I think it will have the same result of the experiment.
Do you change the center of mass? The rod.
We didn't change. You mean that the very center of the rod, or
what about if we change the center of mass, what will affect?
center of mass?
Yes.
Does it mean that if the rod, if there is a very mass like here or like here, what will?
No, it's here and here.
Or you mean that the very center will be like here,
Yeah.
and what will happen?
Yeah.
We didn't change it because basically we cannot fix it on the rod, and yeah, so we didn't do it.
Why don't you put the clay around the rod?
Because the plate might bump of the cylinder, and as we presented, if the rod, if there is a bending moment, so if we put the very initial displacement at here, it is it is more possible to damping and remain static for eventually.
How to control the material of the rod?
We change the material of the rod.
You change the different coefficient of connecting friction.
Yeah.
It will be like this, right?
Yeah. In our experiment, we can see that there is some inaccuracies, and I think it is because of the friction coefficient is measured, and it does not have a real amount, and because it is a part of our experiment too. So maybe the cause of the inaccuracy is because of the friction coefficient measured is not accurate. So yeah, next slide.
Do you think if you change a rod, turn into a tube?
You mean the tube is the center or
the pipe?
Pipe, yeah.
Do you think about it?
What real setup? Or you mean that there is nothing in this inside? In art, yeah, it is nothing inside. Yes.
In your experiment, how do you change the new cable?
So just change the different material, and yeah, we will measure it by this one.
You done?
Yeah.
Okay, so you got 1 minute to summarize your discussion with the board. 1 minute.
Reporter said that the method is wrong, not and it will have a static friction in a moment, but the report said that it will affect obviously. And the massive means it won't jump up. Only vertical and but not real. The reporter checks to see if the staple is flat every time they do the experiment. And the damping is the decay of amplitude.
Thumbs up. Questions from reviewer? You got 3 minutes.
All right. Hello, I'm Eric from Taipei American School. I have some questions. First of all, for the reporter, you mentioned that you have a constant energy that dampens over time. Why would this still be the case? Why would this be the case, considering that we have a applied external force of the wheel itself? Because we're using motors that constantly providing speed. So shouldn't they also add their own energy that can?
If we drew into account, because it is not constantly, because the resultant force at here would be 0. So this will be the energy that the resultant force has done for the rod at the first half of displacement. So virtually it will be the same. But this is the actually there
Reporter, please short answer. Right?
Okay.
Okay.
Effective review.
Right. Okay. So you mentioned that you tried to search for amplitudes, and you said what affected the amplitudes?
the initial displacement of the very center.
And things like mass and angular velocity had no effect.
If it is has the same angular velocity and the same mass.
Okay, I gotcha. Thank you. So another question I have is, have you considered finding the motion of the object in 2D? For example, you have a it's like you have a, for example, square on top of two cogs, and it's like the same thing, but now it's a y direction that's parallel to the cylinder. Do you think there would be a big effect?
Basically, we just use the rod, and we can see as a two dimension. Yeah. So we didn't do that.
Now, you mentioned that you use different materials for the rods. How about would the different materials having different masses yet the same size affect the way that the oscillation works?
Basically, we would take it at the center of the very center of the rod, so we can control the mass.
Right. Okay. And one more thing. Never mind.
You give about 2 minutes to prepare for your next stage. Excuse me? Your time for 4 minutes?
all right. So, hi, I'm the reviewer, and we're going to be talking about the problem 13 friction oscillator, which is the two wheels and the rod. The reporter talked about the phenomenon of the oscillating movement, and how if the wheels are moving in an outward direction, they will not. There is no motion. The theory states that amplitude. It's based on simple harmonic motion, and the amplitude depends on the initial displacement. And the experiment contains 2 cylinders and 2 motors. While I agree that there's good experiment and computer theory I think there should be some consideration over the fact of, that there's two motors that may not have perfectly like consistent speed with one another, and the fact that neither team has mentioned much about the 3D model of the experiment. So on the opponent's side, they questioned about several things like defining mass and jumping of the rod. And while I agree that this is it's very good to include these points and talk about other things like mass, amplitude, and static friction, I think there are some things in their presentation that kind of seemed a little irrelevant to the point, and also they didn't really provide their own opinion for against the reporters. So one thing they discussed was the amplitude and how it changes over time. Reporters said that there would be no change after a certain period of time, which is true. I agree is true, so long as the coefficient of friction does not change. The opponent brought up static friction, and the reporter said there is no effect. However, I feel like if there may be situations where the rod is moving at the same speed as the wheel itself. Thus, in a relative sense, the rod is not moving compared to the cylinder, thus creating static force that could increase the force and thus change the motion. Next, regarding changing mass, it was not the reporter's focus. However, I wanted to mention that the center of mass would oscillate between the two cylinders in a simple harmonic motion. So it's important to consider what happens when the mass goes out of the cylinder. Okay, and points missed. There was they didn't mention how they kept the rod a constant density, and they didn't try using different kinds of rods besides just circular cylinder ones. No one considered the 3D motion, like would it be chaotic now that there's a wide direction they can go through. And rather than using two motors, it might have been better to use something like 2 gears so that the motion's always constant, in my opinion. And can the amplitude be so big that the rod partially rises? I believe that it would have some effect. All right then, thank you.
You done? Great, thank you. So reporter, you got 2 minutes to make a concluding remark.
And the actual motion of the phenomenon is a damping motion instead of the simple harmonic motion, because there is some drag force such as air resistance. And the vertical motion of the rod is a simple harmonic motion. And the reason for the result to fit the motion of simple harmonic motion is because that we only consider the motion at the beginning, and the rod hasn't been affected obviously by the air resistance or the other drag force. And the period of single rotation of the rod will be affected by the friction coefficient and the length between two cylinders. And the initial displacement will only affect the amplitude, instead it will not affect the time of each period according to simple harmonic motion. And the rotation direction will affect the result. And we define the massive object as the rod with a mass that wouldn't affect the RPM of the cylinders, as well as the rod will move vertically, such as the bump up. And we have mentioned the comparison between the vertical result and the actual motion. And we have ensured that the surface is flat horizontally with the accurate apparatus. And in the kinetic friction effect, mostly to the experimental data. And the reason for the measurement of friction coefficient in the same angle is due to the efficiency. And it is too large. The too large mass of the rod would affect the stability of the motor. And the RPM from both sides of the cylinders will be constant, since that we have used the controlling panel. And replying to the opponent and the reviewer that it is impossible to have the same velocity of the rod that another side normal force will change periodically. So it is conflict that if the motion of the rod is taken by the static friction. And this is the end of my concluding remarks. Thank you for listening.
All right, thank you. Comes to questions from jury member.
you know that coefficient friction is kind of important parameters here. So and as we see here, the range you get here is from 0.1 to 0.5.
Yeah. Because
So the question I have here is that how would you do if you want to approach it even smaller
you mean that the
coefficient friction?
basically
Or
find
heavier
the
than, not heavier, I'm sorry, or larger than 0.5. How would you do?
maybe we could put the roughness surface such as the paper that have the rough
To make it big, head,
But,
larger.
yeah.
How about the smaller one? Smaller than 0.1?
I don't have the idea.
I believe that you could also apply some kind of coating or surface onto the cylinders themselves, as the idea is that so long as you have two objects rubbing at any way, they should have the same coefficient of friction. So what I mean is like, you could have two really rough surfaces, one on the cylinder and one on the rod, to increase the coefficient of friction. And
I think that's enough. Anna?
It can have this metal sheet on the rod, and it can be the bigger coefficient of friction and small.
Can I speak?
I think that's enough. We're gonna go on to next question from Joe.
Okay, I have a question for the reviewer. When we will also, we have expect, you mentioned we have expect a 3D motion in this question. So
yeah.
what are your opinion about the 3D?
Sure. Okay. I believe that if there is if we analyze in 3D, there is the chance that an object will have its own little torque as it starts to move back and forth, independent of like the x direction. So it could move in a wobbly way that could cause it to move to in the y direction a bit.
Do you agree?
I agree, but I think that the problem statement asks us to observe the oscillation of the one of the two-dimensional situation.
We got it. Yeah.
And if the diameter of the rod is very big, and the rod may jam that device.
I got a question for reporter. I remember you show a data for the oscillatory period versus the omega, the
Yeah.
rotation. Can you show that again?
Yeah.
No, there's a data.
No, not this.
What I was gonna ask is that in the data, it seems to be the omega dependent, the oscillated period. But in your theory, I don't see any omega in the formula.
Because I think that it will have a deviation is because that the angular velocity cannot conquer the static friction initially. So basically, if we wanted to let it be oscillation, and we need to let it be connected friction. So we just control the angular velocity of the cylinders as 200 RPM here.
But why is that? I mean, and the lower.
I mentioned that the deviation is because the low angular velocity cannot conquer the static friction initially, so it will not be as a periodical oscillation.
Okay, all right, thank you. Any more questions? Yeah. Can I ask? Oh, okay, no more questions. Come to the gradient time. Already? All right, show your score for reporter. Start from me. Eight, 9, 6, 6, and 7. Here comes score for opponent. All right, start for me. 7, 7, 7, 4, 5, and 5. Score for reviewer. 6, 8, 8, that's 8, 6, and 6. No, that's it. I think that's fine. So we're gonna take 10 or 15 minutes break?
It's up to you.
10 minutes, 10 minutes. It's a bit late. All right. Okay. Yeah. All right. Okay, so Donna, you got 1 minute to challenge the board.
This call, wait until the last. Yeah.
Yes.
Oh,
Number 5.
Oh,
5.
Problem number 5 is challenged. You got it? You got 1 minute? Sweet Mirage.
Would you be like small ones? This looks so good. Bad short.
Yeah.
They're not doing it.
Yeah.
Robert rejected. Back to opponent. You got 1 more minute.
What's the box? What's the number? Doesn't matter. Okay,
But
it
they
wasn't
already
10.
approved.
And it wasn't. Yeah, we. Sorry. Yeah. Question number 15.
Question number 15 is challenge. David Reporter, you got 1 minute. Paper pot.
Actually, we didn't prepare this.
So you're going to reject it. Or reject it again. Back to
How many
the
have they
opponent.
rejected? Wait. Can you scroll down?
Question number 3.
Question number 3 is challenge. Reporter, you got 1 minute.
We accepted that.
Yeah, problem number 3 accepted. Now, reporter, you got 5 minutes to prepare for your presentation. Oh, please write down your
I need to have the question, so I should just take the. Oh, go right here now. I know. No. No. Whatever main points is. Yeah.
是啊，挺棒的。没有的话就要换手机。有。最近他们在地震。
This is Excelsior. Okay, you see Excelsior? There are some points are 0 point. They don't. Yeah, there is. They rejected 2 already. It doesn't matter. You can reject with reasonable cause. You just get multiplied by lower. That's the whole point. No, if you reject 3, then all your points. If you reject the 4th one, then all your points is multiplied by 0.8. If you reject more, it's much more points. You already have the 4th one. Pretty much means.
1个礼拜之后，芝加哥的语言都会考。2个就都在芝加哥念书啊。
I just hope we're told that. We were so lucky when we were against America. We were so lucky on the words of the bus.
We're gonna start it? Yeah, you may begin.
Okay, honorable jury and fellow debaters, this is a reporter from Team Diandao Xiaxiao. And this is the question I will be reporting. It's number 332. And this is the outline. And our introduction is about problem statement. I won't read it, but the main parts I think are corrugated is important, spin around is important, and the characteristics is important. Okay, key points, what produces the sound and what is the role of corrugation on the tube. Okay, this is our observation video. So we took a student and we spun the tube with corrugation and just a regular corrugated tube. And as you can hear, it makes sound. And the faster you spin it, the higher the frequency is. Okay, and this is without corrugation, no sound at all. And so the property we observed is that only corrugated tubes create these notable sounds, and the frequency of the sound goes higher when you spin it faster. So our result is that corrugations are essential for the phenomenon, and the production of sound is closely related to spinning the tube. Okay, this is our preliminary experiment. We wanted to know whether the airflow was a necessity. So we took tape and we sealed the mouths of both ends of the tube. And then we proceeded to spin it, and no sound is produced, which means that air is a necessity. Okay?
this is our theories. The first is a theoretical model called sound production. The idea is that when you spin it, due to centrifugal force, the airflow will flow from the inner towards outward. And after the tube has begun to be spun, the air will flow outwards. And the airflow is disturbed by corrugations, which means that when it flows through, it will create vortices in all these corrugations, which will cause a spectrum of sound. Yeah. See? Okay, this is another hypothetical model of selective amplification. In the spectrum of sound produced, only several specific frequencies are amplified, and which directly results in us actually being able to hear the sound. And the idea is that, so it creates a spectrum of sound, but only special frequencies that, we'll explain that later, but only special frequencies will be selected, and these frequencies will be amplified. So we will be able to hear the sound at these frequencies. So this is the idea. It's amplitude to frequency. This is the initial idea, and then due to resonance selection, it will become this picture. And as you can see, there's a very obvious peak here. This is where we will be able to hear the sound. Okay. And the amplified frequency is the natural frequency of the tube itself. Okay, this is quantitative description, so the Scroll-Hall number. So the Scroll-Hall number, ST, equals FB over U. F is the frequency of vortex shedding, U is the flow velocity, and B is the wavelength of the corrugations. And this is the reference, which will describe this. This is what we got from the reference. Anyway, so the idea is that the wind will flow with great vortexes, and this will help create sound. And the frequency produced by vortex shedding is proportional to the flow velocity, as you can see up there. So the theoretical model of sound production. Spectrum of frequencies from the vortices. The wind speed will not be constant inside the corrugated tubes because the flow is turbulent. But so not one but an entire spectrum of sound will be created when you blow air through the tube. Okay, yeah, this is the general idea of how air will flow. Quantitative description, another idea is standing waves. And a standing wave model can be used to calculate the natural frequency of the tube. This is the original equation of standing wave. This is the formula for speed. And so if we add these, combine these two, we get this formula. Okay, this is our setup. The devices we use, Potter's wheel, that you can just sort of read this yourself. Okay, this is more important. So this is the Potter's wheel. We secured the tube to the wood so that, because we were afraid that when we spun it, the tube might go it might grow longer or shorter during our spins. So we secured it to the wood so that we wouldn't have this problem. And as for that is like the literal idea for what it is. It's like would the same phenomena occur if we did not spin it. Okay, this is experiment 1, that's actually experiment 2. These are other devices and the software we use. These are experiments. Okay, so first we did another preliminary experiment, which again is discussing the airflow. So as you can see, it's very obvious. We sealed the two ends with plastic bags. So as you can see, the outer bag right here is contrast, so it's very flat. But after we spun it, it blew up. And since we sealed it, it means that the air had to go from the inside back out, which proves that air does flow through the tube. Okay. This is our experiment 1, wind speed to spin. So the idea is that, as in the devices, one experiment we spun it, the other experiment we just used a tube and put wind through it. And so this is our result. Okay, so the relationship between wind speed and rotation speed can be simplified as this formula, and we calculated the radius of the tube to be about we measured the length of the radius of the tube to be about 0.0925, but we calculated the radius through our theories, and the result was 0.09, which means that these two numbers are actually very similar, which means that we can assume that is correct. Okay, this is our experiment 2, the idea of Strohal number. Because from the references, the result was that the Strohal number should be around 0.39, but when we actually did an experiment, it was just sort of like all around this line. But eventually, the average amount is really 0.39, so we decided to stick with it. So ST shouldn't be significantly affected by the change of wind speed or the tube radius, as you can see. Okay, this is our experiment 3, selective amplification. So in the standing wave model, the peak frequencies are n times the fundamental tone f0. So f equals nf0. F0 is related to the geometry of the tube and the flow rate. So f0 equals 2L prime under V. Okay, and this is our graphs. So as you can see that the frequency to n is very close to 1. So y equals these numbers. Okay, this is our experiment 4, natural frequency. And the result is that this is 0.059, and which is here. In the previous experiment, we tested that f0 equals 2L prime under V. And so in this experiment, we used reciprocal of f0 and the effective tube length to make a graph. And the slope of this graph is the f0, so we can calculate the f as about 339.2. Okay. And this is the real, the supposed wind speed of air at 25 degrees C. And as you can see, it's about 346 meters per second. The result we came up with was 339.2, which is pretty close. The error was only about 1.9%, so we decided it was correct. And so from this, we can calculate the L prime and the K. The K is about 3.5. Okay, so our conclusion, of course, criterion of the phenomenon, the tube must be corrugated in order to produce sounds. That is okay. And also airflow within the tube is also critical. Okay, conclusion, the mechanism. Okay, so when spinning, the air inside the tube is accelerated by the this force. So the air will flow from inside outwards. The corrugation disturbs the airflow and causes vortices, which helps create sound. And so this sound is actually a spectrum of sound, but of course only specific sounds are caught. And it's due to vortex shedding and non-constant flow velocities. Okay, this is the graphs from the experiment, just copied back up. Okay, so the production sound is filtered by the tube through resonance, constituting a selective amplification, which, as I mentioned, it selects a specific frequency, amplifies it so that we can hear, and the sound is heard by our ear. Okay, this is our conclusion and the corrections, like some flaws we discovered, and we decided maybe we could change it. Okay, generally the errors came from 3 points. One was the measurement, because the width of the frequency peak and the geometry of the tube is not always accurate, so we had to change it up. And this may cause errors. And 2 is the speed of the sound, which is dependent on temperature, humidity, and wind speed. We tried to secure this as best as possible, but there is still a slight error. And finally, wind speed itself, the complexity of wind speed inside the system, which we cannot quantify at all because it's inside the tube. And yeah, that's it.
Right, thank you. Now comes to questions from opponent to reporter for 2 minutes.
So did you consider the effective speed of sound inside the sound tube? Like is it the same as outside? The speed of sound the same inside and outside?
Well, it shouldn't, because the wind speed inside the tube is actually different.
Oh, it's the speed of sound.
Yes, I know, but the wind speed is different, and that actually affects those sounds, so I don't think it would be so.
Okay, have you considered the Reynolds number of the system?
Yes, we did. The Reynolds number actually has some effects on the ST.
Okay, do you know, you cannot have the value. Do you know what it is?
I don't think we put it here.
Okay, so in slide 22.
Oh, sorry.
What speed? What speed?
Where? This?
Yeah.
B is wind speed.
How can the wind speed be 339 meters per
you using a fighter jet?
No.
Like that's the speed. That's like close to the speed of sound.
Oh.
Okay. So is the air constant throughout the tube?
No.
Is air speed? Sorry.
No, it's not.
Okay. Does your theory have any limitations? What are the limitations of the theories?
Our theories on actually it does.
Okay. Did you hear your fundamental frequency? When
Yes.
Yes?
Yeah.
Okay. That's it.
All right, you got 3 minutes to prepare for your next stage. Right, only your time for up to 4 minutes before going into discussion with the reporter.
So the point, I think this is the opponent's ideal structure of investigation. So investigate how the sound, how the propagation, splitting in the propagation affects the sound. Analyze the turbulent flow and the resonance of the sound. Develop an equation for the frequency of sound, and determine and test the relevant parameters, which are propagation, spin, and yeah. So the pros and cons of the report. The pros is that
Could you step on the right hand side? Because
Here,
you brought
this side,
heavy.
this side.
Yeah. The pros is that they identify the air as a necessity, flow of air as a necessity. They identify that the swing sound creates a spectrum of sound. Also, they mentioned the stroke number. The concept is that the flow of air through the should be caused by Bernoulli's principle, not centrifugal force. The Strohol number should change with different geometries. And in slide 10, where the Strohol number was said to be kept a constant, does that implies that you only use one kind of swing sound, which is not that good, because different parameters like radius, the corrugation size, the length, the distance apart from the corrugation, these parameters should be considered. Also, the Potter's wheel is not an accurate way to maintain a steady velocity. You should use a motor. Also, in theory page 19, they should use Bernoulli's principle to justify the linear nature. Also, the time management is very dubious because they spend a lot of time on the computer and it's not necessary. So the points to be discussed in the future is the effective speed of sound the same inside and outside of the tube? Does the Strohol number change? How does the harmonic frequency jump from one frequency to another? What do different types of correlations change in this system? Okay. I would like to show this.
Okay, go ahead.
So topic 1. Is this effective speed of sound the same inside and outside? And what does that affect?
No, it isn't, because as I mentioned, when the wind flows in, it becomes turbulent, so it's actually really difficult to measure it, but I don't think it's the same.
Okay. Can you go to the slide where you show the frequencies, the resonant frequencies? Yes. Oh.
So not this.
Yeah, I get that. Resonant. The resonant frequency. Like, how did you determine the resonant frequencies? Can you describe it to me? Like, how did you determine what the resonant frequencies are inside the sound signal?
We determine the natural frequency.
Yeah, okay, then how do you do that? Can you show me the slide?
I don't know where it is.
Okay. What did you show it in your presentation? That's something that I think you should show in your presentation in the future. But the resonant frequency should be n divided by 2L multiplied by the speed of sound. So it should be this equation here. N divided by 2L multiplied by the speed of sound. Okay. So is the speed of sound relevant? How is the speed of sound? Is it different inside? And if it's different inside, you need to account for it. Like, how would you account? Because if you think about it, when the speed, the inertia of the cavities around the thing actually stop, make the speed of sound a bit slower. Did you account for that?
No.
Okay. So how do you think we can account for it? I think you can use this theory. Like, you need to correct for the speed of sound, because the inertia of the corrugations actually cause the speed of sound to be slow. So you need to have a correction term. I would recommend that you add this correction term. Go ahead. So does the Strohol number ever change? Specifically, go to slide 15. Sorry, no.
Slide before.
Yeah, this one. Does the Strohol number ever change? So is this in one sound tube only?
Yes.
Why didn't you use different sound tubes? Did you test?
Because we wanted to secure a lot of parameters that might be caused if we change.
Did you test parameters like the radius of the sound tube?
No.
Well, if you change the radius of the sound tube, what do you think would happen?
Well, I mean, it would be bigger, so the wind speed might be a bit slower.
I disagree with that point. I disagree with that explanation. So, since the cross-sectional area here increases, the effective speed of sound is closer to the actual speed of sound, so the frequency should increase. So with bigger radius, we should expect a higher frequency.
Higher frequency.
Yes. Okay. So how does this? Did you test? So did you, for the entirety of the experiment, did you only use one sound tube?
Yes.
What parameters did you test?
These rotation speed
Uh-huh.
and
But how is rotation speed different from frequency? Like what is the two difference of that? What is the difference between the two?
one is spinning and one is rolling.
Okay. Were you able to measure the velocity of air inside the tube when you spun it?
No.
Have you considered using an anemometer and then
Yeah.
attaching it in the back and then spinning it that way?
In
It's
the
just
back?
yeah. You attach an anemometer, put it inside the sound tube and just spin.
The problem is we don't have any anemometers.
Okay. I recommend you buy an anemometer and test that. Test it that way. In order to confirm that your theory, your assumption that it is linear is actually correct. Because I remember you had a slide where you show the wind speed inside the tube is linearly related to the wind how you spin. Oh yeah, also in slide 17, in slide 22. What's V?
Oh, correction. It's the speed of sound.
So it's the speed of sound, okay. So as you observed there, the speed of sound is actually less, right?
Yes.
So you said that your theory is correct because the speed of sound is, even despite the fact that your speed of sound is less. Could that be accounted with my correction term? I think that your theory is actually not correct and it actually needs a correction term. This is the proof. Yeah.
Wait, so what is the proof? Because our idea was that.
So what I said is that the speed of sound inside the tube is actually less than the speed of sound outside the tube because of the inertia caused by the corrugations. The air inside the corrugations has inertia, right?
Yes.
And the speed of sound there is 339.2, right?
Yes.
It's less than actual speed of sound, right?
Yes.
So this supports that we actually need to account for this. It's actually a significant number. Okay?
So it's actually
Okay, you get it right? Thanks. Thank you. So what do different types of corrugations actually change? Like if you change the corrugations, what will happen?
How do you change the corrugation?
You get a new tube.
Well, unfortunately, we never tried.
Well,
Maybe we should.
what is the discussion? You can still say it. Okay. I vote. Take a wild guess.
Well, we did this one, but it's not exactly the same. We did try the amount of corrugations.
Amount of corrugation?
Yeah.
Okay, so what would it change in your system?
It would change the amount of corrugations.
Well, like, of course you'll change the amount of corrugations, but how would it affect your results?
The frequency would actually be higher.
Why would the frequency be higher?
Well, the idea was that we took a 190 corrugation tube and we just like spun it and tested the frequency. And then we cut off 10 corrugations pulled it to the same length and did the same experiment. And so on in terms
So,
of.
so that you observe that the frequency was higher? Yes, but how would that make sense? Because if the length of your tube is constant, then your harmonic frequency should be the same, despite having different corrugations. Okay. Well, then, do you have an explanation for that?
No.
Okay. I'm not sure what happened there, but the answer I wanted you to give was the different types of corrugation changes the amount of your Shoho number. The Shoho number will change with the amount of corrugation. So you might have to, so the velocity input into the tube, and that may be more or less, and then you get the same frequency.
Wait, what?
Like, since the frequency of shedding is equal to is proportional to the velocity, right?
Yes.
With the velocity, if the Shoho number increases, then you need a lesser velocity to reach the same harmonic frequency, right? Yeah, so that's how different corrugations will change the system. Some corrugations are better than others, and that you can spin it at a slower speed to produce the same sound as if you have less good corrugation, right? Yeah, I'm just saying that's true. Okay, you should try varying the parameters like in the future you should try varying the parameters like the volume of the corrugations, the distance between the face of the corrugations, the radius of the tube, the length of the tube. Did you cut the tube and see the frequencies?
No.
Did you only have one sound tube?
Yes.
So did you not afford to cut the tube and see if the thing changes?
Pretty much.
So you couldn't do that?
We couldn't.
Okay, that's unfortunate. So, oh yeah, did you calculate a Reynolds number?
No.
I thought you said you did before.
Well, we got the Reynolds number from the reference.
Oh.
And the reference told us that at a very large range of Reynolds number, the S2 would remain about the same, so we just accept it.
The discussion.
All right, yep. Thumbs up. Well, you got 1 minute to summarize the discussion.
So the following statement asks you to change the relevant parameters of your experiment. You clearly do not change the relevant parameters. The only thing that you tested was the wind velocity. You could have tested the radius of the tube, the volume of the corrugation, the distance between the corrugations for the pit length, and you could have changed the length of the tube. You could have changed the sources of air, like for example, does the air compressor make a difference in a fan? But in the end, you only changed one parameter, which made the discussion rather hard. Also, your theory was quite incomplete in that it didn't account for the electric speed of sound. You didn't, and you didn't. Thank you.
All right. Now comes to question from reviewer to reporter and opponent.
Hello, I'm the reviewer from Team Celsius, and the first question is that reporter has mentioned in your
Take a
report.
floor, please. Reporter and opponent, take a floor.
In your report, I mentioned that the corrugate is necessary of this phenomenon.
Yes.
Because it will cause the vortex in the corrugate. So the sound we heard will be the vortex, the frequency that caused by the vortex. You agree?
Yeah.
And for the opponent, you agree?
The frequency is caused by the vortex shedding, and if the frequency resonates with the natural harmonic frequency, then it will cause an amplifier. It will amplify.
Okay, thank you. I agree with the opponent. And for the reporters, that where did you put your microphone when you're doing the experiment? In the center or by the side?
In the center.
Because you want to reduce the Doppler effects.
Yes.
Okay. Do both of you think that do you think the sound was do you think the sound will stepwise increase while we increase the angular velocity of the tune? The sound will stepwise
intensity.
like the frequency will be like this while we let the angular velocity become faster.
Yes.
So you do think it will be like this? Okay. Because you use the open pipe formula to explain this phenomenon. Because we use the tune sound aggregation, so it's a little bit different for this formula. So do you do anything to fix the difference between these two tune? No. Do you think it has to be fixed?
Hold on, I didn't quite understand.
Because the open pipe the formula is for the normal tune, but in this experiment we use the aggregation tune. So do you think we have to add some things to fix this difference between these two?
I think you have to account for the relative speed of sound.
Okay, thank you.
The effective speed.
Also, for the opponent that you had mentioned that when we use the same end of the tune, so you're in the same harmonic. So if also you say when we change the
It should be approximately.
yes, also when we change the curve gate, what we have what kind of change would we have?
So little mistake there. If you change the tune, the harmonics would change, but it would change very little. The reason why the harmonics will change is because
Okay. The meaning of is when we change the corrugation, what will change? I know the harmonic won't change, so what will
the
change?
harmonics could change because the effective speed of sound.
So think we change the corrugate, the harmonic frequency will change.
Yes.
Okay, thank you.
All right, hands up. You got 2 minutes to prepare for your review. All right, you may start.
Hello everyone, I'm the reviewer from Pink Research. Today I'm going to review problem number 3, tune sound tunes. First statement, a sound tune is a toy consisting of a corrugate plastic tune that we can spin around to produce sounds that the characteristics of by such choice and the effects of grammar parameters. And main focus will be on how the corrugate, sound corrugate and how the sound affect by grammar parameters. And here's the reports outline at the conservation video. You can see the phenomena happens, but they didn't mention in their report that they have calculated the different radius of the Doppler effect, and their theories they say about they use the open pipe harmonic to explain it, but they didn't fix the difference between the normal tube and the corrugation tubes. And at the experiments, I think they didn't do the main things, the main factors that we're going to get in this experiment, which is the frequency of stepwise increase like this, or why will the sound be produced. And also, they think the frequency we heard will be a vortex of frequency, or it will be the vortex of the frequency that the corrugation produced, but the real things it isn't. And the discussions do good on the BIOS controls, and also, but he didn't do well on the first explain the information between the theories. And here's the opponent's pros and cons. He talk about effective speed in the tune, which is different from the outside. I agree with him. Also, the types of the generates, which is the main factors of these phenomena, and also the frequency leakings. And he gave opinions about the whole of the qualitative of data, and also discussed about limitations of the phenomena, and also he very strict questions, and also sound velocity in the tune is different than outside. So I think the opponent did a great job on talking about the main factors of these phenomena. And but he didn't use, but he fails to clarify the phenomena, and also the speed of the official speed is too fast. And there's a discussion which is the sound velocity. And the opponent asks about will the sound velocity in the tube will different than outside, and the reporter say no. But I agree with the I think that the sounds in the tubes will be different than the outside, because there will be the airflows in the tube, so the sound velocity will be different. And the second they talks about the radius and the velocity. And it turns out if the opponent asks you take the radius of the sound tube, and the reporter says the radius increase, the wings velocity will decrease, which the opponent didn't agrees with the reporters. But the real thing is that when we use the same angular velocity to swing the tube, when the diameters of the tube is bigger, the flow velocity in the tube becomes lower. So the frequency we get will become slower. Well, the frequency we get will become lower. And the discussion see they talk about the coefficient types, and the opponents ask about different coefficient types. And the reporters say they didn't try. And I think the reporter should try, because which is the corrugation's difference and also the length difference are the main factors to if this phenomenon happen. So it has to be tried in the experiment. And that will be the point is the first will be the condition to produce sound easily, and also the second will be the sound, the risk of sound wisely increase. They'll talk about the sound stepwise increase, but they didn't discuss about why. And also, can we predict the boundary conditions to leak when the sound we're going to leak like this here? So they didn't talk about the conditions. And also the leaking height condition, which is the height of at here. They didn't talk about it also. And they didn't say about the. Thank you.
Excuse me, time's up. Reporter, you got 2 minutes to make a concluding remark.
The remarks is the original conclusion: the tube must be corrugated, there must be air, and the airflow. Okay. And we learned a lot of things from the opponent. We will try to introduce a lot more parameters in the future. Okay. So the effective speed inside and outside the tube is different. The resonant frequency is determined on relevant to the speed of sound. The Strohal number is the quotient change for the change of sound. And according to the theories informed by the opponent, the higher the radius, the higher the frequency. And okay, the sound we heard is caused by the vortex, and it resonates with the tube in the front. Okay, and the opponent presented the Bernoulli's formula to discuss the airflow, which we will use in the future.
No? Yes. All right, great. Please take the floor. Questions from jury members?
I have a question for the opponent. You mentioned about the difference between the Bernoulli effect and the centrifugal force. What is the major experiment evidence that you provide to distinguish these two effects?
So to conduct an experiment,
How do you differentiate these two costs by the experiment? Or anyone of you have answered that also provide.
Remember,
Did you restate the question?
Okay, the opponent mentioned about the Bernoulli effect, also the centrifugal force, which is your reason of producing the states. So do you now think he's right or what? You think it's
reviewer,
Bernoulli effect?
you're gonna go first?
I think the Bernoulli predictions isn't the main factor, so for the correlation term to produce counts.
Do you agree with me?
No, I think this is not the main factor.
Not, then what do you think is the
I think the Bernoulli prediction is only to explain why the airflows will go through the tube, which is when we spin the tube, the flow rate speed outward will be faster, so the pressure it will be close to the pressure difference. So the airflow will go through. So I think the Bernoulli's prediction is in this experiment is to explain why the airflow directions in the tube.
You want to answer something?
So I think that at the beginning, like when you just started turning it, it might still have a little bit to do with centrifugal force. But after it starts spinning, when we start spinning it, there's actually a height from which the air will go, which correlates with the Bernoulli principle. So I think that after it begins spinning stably, it might have something to do with the Bernoulli principle.
I think the Bernoulli principle has remained effect. I honestly do not know how big a role centrifugal force can play on this. I tried to think about it, and I think that.
Could you think of a way to test this phenomenon? The Bernoulli equation, Bernoulli phenomenon does really play an important role.
Moment of inspiration. Have the two tubes, right? Then use a line as pressure meter along the.
Where's the pressure flow?
Huh? Okay.
When you are spinning, where's the pressure flow?
The pressure?
When you spin it?
No. Can I draw that?
Okay. Better make it quick.
So to close the two ends, right? Add pressure sensors along here. And then spin the tube within close. If the pressure here is higher than the pressure here, then the centrifugal force may have a greater effect.
All right. Any more questions? Yes.
I'd like to come back to this controversial issue on the you enlarge the cross section. Yeah, that the opponent proposed, but we get different answer. I'd like to start with the reporter. What is your final view on this issue? When you enlarge the cross section, will the tongue be increased or decreased?
Well, I
and
think
why?
I
This
think
is
it will
for real reason. Please.
I think it will increase.
So you're convinced.
So it's about the diameters of the tube.
Right.
I think that the diameters will become bigger and the flow velocity in the tube will become slower. So the vortex, the vibration of the vortex of the frequency that produced by the propagations will be the vibration of air will become slower. So the frequency will get become lower.
Right.
I think that the reviewer does have a point. I think that if the velocity of the air inside the sound tube is constant, I think the frequency will increase because of the correction factor. However, realistically, when we're spinning the sound tube, the flow of air into it is a bit more complicated. So I think that the change in geometry may actually impact the frequency of the sound.
In what way?
Huh?
In what way? There is always impact.
Actually, it's right.
mind. I think that.
I-
Okay, yeah, give me
no, no.
10 seconds.
I'm going to, I agree with my original answer, that the frequency will not change. Even if the velocity is slower, it will only jump from harmonic. Sorry. It will only jump from
alright.
harmonic. Yeah.
Okay, thank you very much.
I got it.
Okay, grading time. You ready? Okay, I'll show your score for reporter. Start from me. 6, 6, 8, 6, 5, and 5. Score for opponent. Start from me. 8, 8, 9, 8, 8, and 7. Thank you. Score for reviewer. Red score. Start from me. 8, 8, 8, 8, 6, and 7. All right. So, in general, any comments from jury members? Just for educational purpose.
This is educational for me.
That's good.
But I mean, it's happy to see, I mean, of course, different factors comes in, so one may increase and the other may decrease. So the reality, maybe we need to do it more, not maybe, we have to do more.
All right. Good. Any other comments? If not, I'd like to close tonight's session. Thank you all.
Thank you.